and circuit model, Webinar, model, model. Okay, so far we covered superposition. I also assigned homework problem for next Tuesday to practice superposition and source transformation. Both of them are kind of short methods, not too many guidelines, just keep one source at a time, kill the other sources, and go through circuit analysis and find the quantity and add them up. Do you have any question about anything before I start? Any question about any topic, any material, any problem? Okay, so let's continue with source transformation. I decided from that last lecture that I'm not going to ask any question. I just continue my lecture. However, because of course policy, I do take role. Sometime maybe in the middle of the lecture, or beginning or the end, look at the Zoom list because attendance is still part of the course, but I'm not going to ask any question from anybody. So let's continue with the source transformation. Okay, the concept of source transformation is based on a very, very simple observation. This observation is the combination of, it's basically its own law, but we express it this way. Anytime you have a voltage source, dependent or independent, it doesn't make a difference. Let's say we have a voltage source V in series with a resistor. You must have a series resistor. So look at this pattern. The pattern is a voltage source in series. This is terminal A, terminal B. This symbol in mathematics means equivalent. It's the same. So this combination generates the same energy as, would you please, if you don't have any question, please mute your mic. At least for my earphone creates very disturbing noise. So you can always convert voltage source to current source. Let's call it I. However, once you convert it to the current source, you have to place R in parallel. So if you're looking to the left of terminal AB, this combination is the same as this combination. It's the same. So if you have a current source in parallel, we can always convert it to a voltage source in series. Vice versa, if you have a voltage source in series, you can convert it to current source in parallel. What's the relationship between V and I? Same as Ohm's law. V is equal to R, or I is equal to V divided by R. Okay, this method is called source transformation, and it makes many problems, circuit analysis problems, much easier to handle. I'll give you a few examples, and if you have a question, please ask, and then I'll give you more examples if you want, related to all material that we have covered so far, and then we move on to voltage, to the northern equivalent. Okay, this is basically the meaning of source transformation. A voltage source in series is the same as a current source in parallel. Okay, let me give you one example. This example is a class example, so please write it down. It's from the book. Let's say the following circuit is given. 12 volts, 3 kilo ohm, and then we place a current source here, 2 milliamp, and then there is another 4 kilo, and then there is another 2 kilo. Okay. Suppose they ask you to find voltage across 2 kilo. Find VCO. You have many options. First of all, you cannot combine these two. You have many options. You have nodal option. You can use, you have mesh. You have superposition. You have KVL, KCL, which is not wise thing to do. But let's apply source transformation. In the exam, if I give you essay problem, I specify the method. And you have to use the method. Like, for example, if I give you this problem and ask you to find V0, and you use nodal and get the correct answer, you don't get any point. Because in the exam, this upcoming exam, the main thing is to test you on knowing the method. So you have to use the method that's asked in the problem. So for source transformation, question is V0. Go to the end of the circuit. I do see a voltage source in series. So based on source transformation, I can change it to a current source in parallel. So this is 3 kilo ohm. Ohm remains the same. What's the value of the current? 12 volt divided by 3 kilo ohm, which is 4 milliamp. Continue the rest of the circuit as it is and do it one at a time. So I continue the rest of the circuit, nothing changes. I'm just changing this combination to this combination, 2 milliamp. OK, and 2K. Okay. Now, notice that I have two current sources in parallel. I can combine. 4 milliamp is going up, 2 milliamp is going down. So the net value is 4 up, 2 down. So it's equal to 2 milliamp up. I can simplify as 2 milliamp up, 2 milliamp up. No other changes. 3 kilo ohm, 4 kilo ohm, and 2 kilo ohm. Notice that I'm making one change at a time. So first I change this voltage source to current source in parallel. Then I combine these two current sources. They are in parallel location. You can move these 2 milliamp here, combine, and substitute by 2 milliamp. Okay. Again, source transformation. Now you see these two in parallel. According to source transformation, you can convert it to series. Any current source in parallel becomes a voltage source in series, 3 kilo. The rest of the circuit is the same, 4 kilo and 2 kilo. And we have plus or minus V0. So I'm changing this parallel to series again. Okay, for parallel to series, resistor remains the same. Resistor doesn't change. The current becomes voltage. How? Amp times 2 milliamp times 3 kilo ohm. So it's equal to 6 volts. This is going to be 6 volts. Okay, by source, back-to-back source transformation, going from series to parallel. Then from parallel, series to parallel, then combining current sources, then I go from parallel pair to series again. So this is my, I haven't changed anything in the circuit. Circuit remains the same. The circuit is fine. Okay, now look at this circuit. It's a series circuit, voltage division law. Now you should be able to find, according to voltage division law, you can find, let's do it here, from this circuit here, using voltage division law, V0 is equal to what? V0 is the voltage across 2 kilo ohm divided by summation of all ohms, 3 kilo plus 4 kilo plus 2 kilo multiplied by the value of the voltage source, 6 volts. So if you simplify, it's 2 plus 3 is 5, 9, and 9, so you get 9 divided by 2, it's 4 over 3 volts. That's voltage, that's source transformation. Any question about this problem? Or wait until you finish all.
I have a quick question.
Yeah, go ahead.
I know this is not necessary here, but if you were to, on the right side where V naught is located,
This one?
yes, if on the top and bottom lines where if you were to extend it and create an open circuit,
This extend this as open circuit is the same.
yeah, is that voltage and for the open circuit the same as that voltage in the resistor?
Yeah, because the reason is because there is no open circuit has a voltage. Usually when they extend the line, that's just the style they use in textbooks. They just want to show that it's not connected anywhere because this side doesn't draw any current. That's why this voltage remains the same. Yes. So if I put plus or minus V0 here, it's the same as this one.
Okay, thank you.
Any other question? Okay. Let's do another problem. I normally involve the students, but as I said, for this class, I decided not to go around because it's not working here. So I just do the problem, but anytime you have a question, stop me and ask. Let's do a few more problems. Are you still drawing this, or should I erase it? Okay. Let's go to another example. This example is from National Engineering Board exam, FE exam, EIT or FE exam. I remember this question. Okay, the following circuit is given. Actually, I'm trying to remember the question. Yeah, okay. Let's do it. This was the question. So let's say we have 2 ohm and 12 volts. 2 ohm, 6 volts. Oh, 8 volts, sorry. 8 volts. Then there was 10 ohm, 20 volts, or 30 volts. Sorry. Then there was a current source going down, 1 amp, and then they have a resistor here, 2 ohm. And the question is, find this. You can't do any method except if you can use nodal is okay. Mesh is okay, but it's not advised because you get too many questions. You cannot combine these voltage sources. You cannot combine these resistors. These resistors are not in parallel because one end is here. They're all connected to this terminal. But from this end, they go to different places. Nothing is in parallel. I mean, branches, I mean, the whole thing, the whole line is in parallel, but elements are not in parallel. The best method, the fastest method for this problem, Because you have overall look of parallel, but elements are not in parallel. The best method is source transformation. So let's do that. So you have to go to each branch, highlight, and convert it to parallel. Notice that for this branch, we have voltage source in series. So for this branch voltage source in series, we can convert it to a current source in parallel. What's the direction of current going from minus to plus? Going up. 2 ohm, and the value of the current source, 12 volt, divided by 2 equal to 6 amp. Extend the line, do the same thing here. You have a voltage source in series. Change it to a current source going down, from minus to plus, going down. In parallel with 4 ohm. What's the value of the current source? 8 volt divided by 4. It's 8 divided by 4 equal to 2 amp. Going down, down because minus is top. Then extend the line, do the same thing. It's a voltage source converted to the current source going up. 30 divided by 10 equal to 3 amp, going up, and in parallel with 10 ohm. Here, no change because you just have a current source 1 amp going down, and no change here. Usually don't change the element in question. Also minus 3. So for 3 branches, I change voltage source to a current source in parallel. Now the next step is to simplify. How do I simplify? I have 6 amp going up, 2 amp going down, 2 amp going down, 3 amp going up, and 1 amp going down. For the down, I put minus. For the up, I put plus. So I have plus 6, minus 2, plus 3, minus 1. 6 amp plus 3 amp, and 2 amp going down, 1 amp going down. So this is equal to minus 2 minus 1 is minus 3, cancel 3 is equal to 6 amp. So this combination, combining with 1 amp, I get 6 amp. So I substitute all of them by 6 amp going up. 1, 2, 3, 4, sources become 1. Now I have, don't touch 2 ohm at the end. I have 2, 4, and 10 in parallel. So I have 2 ohm in parallel with 4 ohm in parallel with 10 ohm. Let's find it. So here R is equal, you can combine any of them first. So it's 2 times 4. So let's do the calculation. You can use the inverse or any way that you can find 3 resistors in. First I combine 2 and 4. 2 times 4 divided by 2 plus 4. So it's 8 divided by 6. So divided by 2, it's 4/3 ohm. Then you have 4/3 in parallel with 10 ohm. So you have 4/3 plus 10 ohm. It's equal to 40 over 3 divided by 34, sorry. It's 30 and 3, 34 over 3. So the total resistance is 40 over 34. If you simplify, it's 20 over 70 ohm. So I put 20 over 70 ohm. And then I have 2 ohm here. You have the option. I show you both options. Do you have any questions so far? This was the FE question.
Why did you say the source transformation is the best method?
Because I can't do anything else. Because notice that if you want to, you can use nodal, but then you end up with equations and unknowns. I mean, you have only one node here. Actually, one equation, one unknown. With source transformation, algebraically, I don't get equation unknown. Source transformation step by step is changing the format of the circuit rather than having equation. But nodal, if you use nodal, you can try to write nodal here. You end up with equation unknown if you use nodal. Otherwise, if you use other methods, mesh, then you have to write 1, 2, 3. You have to get 4 mesh equations. 2 of them, one of them simple, but you get 3 equations to run. If you use KVL, KCL, again, you end up with 4 equations. If you write nodal, you end up with 1 equation. So source transformation, and the reason source transformation is probably better, look at the overall look, just based on drawing. You do see parallel lines. However, inside, on each line, elements are in series. So if you can see, if you can somehow change the series to parallel, then you have overall complete parallel look or parallel format. This is not complete parallel format because each branch has series. If you can change series to parallel, then you have complete parallel format. So without writing any equation, I can come up with my answer. So that's why source transformation, this is a typical example they use in order to show the advantage of the source transformation. Any question?
Yes, Professor. After using source transformation, how do you determine the flow of the current or direction of current?
The direction of the current is always from minus to plus of your voltage source. So for example, in this case, because my voltage source is down, plus is up, the current goes up.
Oh, okay.
In this case, it's minus plus, it's going down. So for source transformation, the direction of the current is matching non-passive sign, like going from minus to plus. You always draw the current when you do the source transformation according to the direction of voltage source going from minus to plus, and vice versa. For example, in this case, if I apply source transformation one more time, I'm going to change the current source to a voltage source. Okay, the current goes from minus to plus. Always check that. And the value is 6 amp multiplied by 20 over 17, and then you put 20 over 17 ohm here and 2 ohm here. Now notice that there's simple voltage division, you can find it. After I covered everything, after we reduced source transformation, gradually reducing the number of elements. So here, from the original 1, 2, 3, 4, 5, 6, 7, 8 elements, we reduced to 3 elements only. So what is V0? Voltage division law is 2 ohm divided by 2 plus 20 over 17, summation 2 ohm multiplied by total voltage. Total voltage is 120, 6 times 20 divided by 17, and then volt, and then you sum. That's the main usage of source transformation.
Professor?
Yeah.
Before the source transformation, have you used current division where the
No,
two
I cannot.
resistors are in parallel?
Yeah, you can do that too. So for example, this is one method. I wanted to show you, this is one method. Once I reduce to this format, you have 2 options, 2 simple options. You can either use this one, or as you said, I can use current division. Let me use a different color, let's say brown color. I can also use current division law, current division. Find this current, I0. What is I0? Is the other resistance, 20 divided by 17, 20 divided by 17 plus 2 ohm, okay, multiplied by 6 amp. Okay, find I0, and then after you find I0, V0 is Ohm's law. It's 2 ohm times I0. Yes, you can do that. You can either convert it to a voltage source, use voltage division, or keep it this way and use current division and Ohm's law. Any question? Okay. So I'm going to start now, Seven and Northern, but let me ask the entire class, whoever is listening. I finished pretty much all circuit methods. We covered everything. For circuit analysis, it's way more than enough. Pretty much you can handle if you're in electrical engineering field, or even if you're in mechanical engineering, and in future you're using any type of electrical engineering related project, using these methods. First of all, you can use PSPICE. I do recommend, highly recommend, and you have to eventually use MATLAB, PSPICE. When you take lab courses, electrical engineering students, they become familiar with PSPICE. In circuit one, I insist on using manual methods so you can get a good feeling of circuit analysis before you use computer tool. The problem, circuit analysis course, when they teach mostly in community colleges, is the fact that they don't cover the theoretical part. They just jump right to the software, and the software computer is doing. The software part is very easy. It's command-based. And once you take a lab board, you can even study on your own. There are plenty of resources, PSPICE, that you can handle. We have two problems with knowing only computer method. Number one, design problem. There are many design problems that parameters are not given. So you have to set up equations on your own. Number two, when you have what they call it, problem debugging, like you have a situation, you are at the field, like especially in power area, and you have to think about what are the possible causes of problem. You have to think about, maybe you have some kind of short circuit someplace, maybe you have some kind of open circuit someplace. Then the concept, you have to know the circuit concepts, and maybe do the quick calculation in order to come up with the answer. Number three reason that you need to know these theoretical stuff, all entrance exams. When you go to graduate programs, you have to probably pass some exams, like a Q exam, qualification exam. When you get engineering license exam, then you have to answer circuit question. They don't give you a computer. They don't even allow you to use smart calculator, just the basic calculator. That's all you can use. So that's the time that you need to have some theoretical knowledge, be able to handle circuits. So that's the whole point of covering all these methods, so you can handle circuit analysis problems. And you learn circuit analysis mostly by solving problems, getting involved in questions and answers, doing problems. That's the only way, because the theoretical part, like chapter 5, superposition, there's no theory, just taking. You just have to consider one source at a time. So there is no, there's nothing involved in terms of doing some kind of advanced thinking or advanced anything. There's no theory, there's no mathematical proof. So I finished main methods, shortcut methods, which is KVL, KCL, and the rest of them, they're all based on KVL, KCL, but shortcuts, voltage division, current division, model, mesh, superposition, and source transformation. And if you're an electrical engineering student, as you continue taking electronics, power, other circuit-related courses, you eventually have to use them, these methods. So I'm done with methods. Is there any question about anything, sir?
Can we do another example?
Of which method? Source transformation?
Yeah.
Okay.
I have a question.
Yeah, go ahead.
Can you use source transformation on dependent sources?
Yes. However, can you apply source transformation This is a question, it's a good question. Dependent sources. The answer is yes, but maybe not a good choice. Until you become expert, not expert, very comfortable with circuit analysis. Students, they lose track when it comes to dependent source. My recommendation, anytime you see a dependent source, either use nodal or mesh. It's less confusing. Okay, how do I apply source transformation? Let's say we have part of the circuit. Let's say we have some circuit, it's given. Part of the circuit, let's say we have a dependent current source. Dependent current source is not a constant value. Let's say it's 2 times some voltage V1 someplace in the circuit, maybe someplace V1. And then let's say we have, I'm not going to give you the complete circuit, just portion of it, because I want to learn the rest of the circuit. And let's say this is 2 ohm. Is it okay to apply source transformation? Maybe, and actually let me change this problem. I don't want to make it too complicated. Let's say we have some kind of, I don't know, some voltage sources, some resistors here. Okay, so on and so forth, doesn't matter. Is it okay to apply source transformation? Yes. However, when you apply, remember, the current source goes to voltage source, but as a dependent source, no problem. If you feel comfortable, that's okay. So you can change this one to a voltage source, current going from minus to plus, in series with 2 ohm. Let's say this is 10 ohm, and then you continue 10 ohm, the rest of the circuit. So you can go from here to here, no problem. But this is equal to the value of the current source. Remember, this is ampere multiplied by ohm. So it's equal to 4V1. So you have 4V1 volts. No, the current source becomes a voltage source. But dependent. So the dependent source, sorry, I disconnected my microphone. Let me reconnect. Okay. So the dependent source goes to the dependent source. That's perfectly fine. Now, here comes, remember, the whole purpose of source transformation was to combine, reduce the size of the circuit. If I had a current source, independent current source, after converting to voltage source, I could combine, let's say this is 4 volts. Okay, after conversion, I still have my 4 volts here. You have 2 voltage sources in series. Is it okay to combine them? Yes. But remember, combination of dependent and independent, you still have to use dependent symbol. It's minus plus. So I can combine this voltage source and this voltage, which is now 4 plus 4V1. And then I can combine like a 2 ohm and 10 ohm, which is 12 ohm. That's okay. Notice that you're not doing anything wrong. The only problem is here. When you combine dependent source to independent source, it kind of makes your function a bit longer. It's a function, it's not a number. If I had like 2 volts here and 4 volts, 6 volts, I could put just 6 volts. But this is a dependent source. And if you have a large circuit and keep combining, and then this expression becomes longer and longer, some students, some people, they're uncomfortable with that. As I said, the answer to your question is yes. Is it okay to do it? Yes, as long as you feel comfortable. But I cannot claim that it's the best choice. Like previous problem, I said this is the best choice. Here, I cannot claim that it's the best choice. Why it's not the best choice? Sometimes due to the presence of a dependent source, it makes it a bit kind of odd looking functions as we continue. It makes it a little bit messier for some people. Is that okay?
Yes, Professor. Thank you.
Okay. Let's go. Somebody asked for another example. I'm gonna assign some problem for you guys to practice on it, but let me see if I can find. Actually, uh, your textbook is making problem. I'm gonna choose one problem that is kind of a bit challenging for source transformation. But I'll try. I'll try. This is kind of a bit challenging, but it's a good practice for source transformation. Notice that there are problems that you cannot have. You must have a voltage source in series. And the problem with source transformation is some people, they don't know how to start. That's usually the problem. This is a problem from textbook. Textbook is always using kilo just to make it more practical looking. Okay. Actually, what I'm gonna do, I keep this example as my wrap up for these methods, for all the methods. I'm gonna keep this example, okay? And apply for all four methods. Source transformation, nodal, mesh, superposition. As a good backup example. So be ready to write all four methods. I'm going to start with source transformation. And actually, instead of kilo, so not worry about kilo, I'm just going to change it to ohm. This is 4 ohm, 3 ohm, 2 ohm, 12 volts, 2 amp. Okay, the following circuit is given, and this is the question. Find R. IZ. Okay, method one, and I have to erase because I don't have enough space here. Usually in class, when you have large blackboard, you can show all four methods side by side, but here I have to erase. Okay, source transformation. For source transformation, I have to go and look at the overall look of the circuit. First of all, do not touch the part in question. Keep it, because it's related to the question. The rest of them, I can't do anything about 2 amp here. But notice I have a voltage source in series, voltage source in series. I'm going to redraw the circuit for each case nodal mesh. For this one, I want to make a change right on my circuit. I have a voltage source in series, voltage source in series. I'm going to change it to current source, new redraw, but I'll do it here. And I'm going to use a different color so you can see the change. I'm going to change it. 6 volt divided by 3 ohm, 6 volt divided by 3, 6 divided by 3 equal to 2 amp. And then I take this 3 ohm from here and connect it in parallel. So I take 3 ohm and connect in parallel. The current source becomes a voltage source, 6 divided by 3 equal to 2 amp. Any question? Okay. What about this voltage source? This voltage source, if I move it here, it's going down. Minus is at this terminal, plus is at this terminal. So the current is going down toward the terminal. So I take this voltage source and change it to a current source. Going down because it has to go this way. It's 12 divided by 6, which is equal to 2 amp. And then I have 12 volt in series. Now I'm going to change it in parallel. Any question? I'm going to clean up. So I changed this voltage source, current source, and voltage source in series to a current source in parallel. Okay, let's clean it up. So I have, okay, now look at the shape of the circuit. You have, I'm not writing any equation. I have 2 amp going up and 2 amp going down because they are in parallel. I can, in this case, it happens that they are the same. So what's the net value? 0. So I can remove both of them. 2 amp going up, 2 amp going down. So 2 minus 2 is equal to 0. 0 amp. 0 amp, anytime you have 0 amp open, anytime you have 0 volt short. So I can just take away these two because they are the same. What about ohm? I have 3 ohm here and 6 ohm here. 3 in parallel with 6. 2 ohm.
So where did the 12 go?
Just, sorry, it's my microphone is getting kind of disconnected. Just give me 1 minute, please. Hold on. Okay, go ahead. Yeah. So what? Sorry.
Where did the 12 go?
Which 12?
There was a
Oh,
12
yes,
ohm.
no. 12 ohm. No, this was 3 ohm and this one was 6 ohm. I don't have any 12 ohm here. Let me see. No, I'm doing original.
It was before you drew the blue line at the bottom.
My original graph, I had 3 ohm and 6 ohm. I don't have 12 ohm. I had 3 ohm here, 6 ohm here.
I think he's referring to the 12 volts that was right there.
Oh, the 12 volts, 12 divided by, I had 12
Oh, that was volts.
volts.
It wasn't ohms.
I had 12 volts and 3 and 6 ohm, right? These two in series, I change it to a current
Okay,
source.
yeah.
12,
Like
12 divided by 6 equal to 2 amp. And then 6 ohm. So I have 2 amp going down and 6 ohm. So 12 volt is converted to amp. So there's no more, so you can erase it. Do you understand? Do you all understand the conversion here? So that voltage source in series is converted to a current source in parallel. The voltage source in series, sorry for the noise outside, they're doing some construction. I can't do anything. I close all the windows, but there is still noise. Then you have a voltage source in series with the resistor, I converted to current source in parallel.
Professor, I have a question.
Yeah.
Something that I don't understand is when we're doing the conversion, why do we still have a 3 ohm? I thought if we do the 6 volt and the 3 ohm,
That's-
doesn't that go away?
That's source transformation.
Source transformation, correct.
Yeah, anytime you have V and R, this is the same as
Yeah.
V divided by R,
Yeah, it goes to current. Yeah.
so you still keep R.
Oh,
R is the
okay.
same. Yeah, R
Okay,
is the same.
okay, I got it. Thank you.
See, source transformation mainly is changing. You have two components: voltage source, current source, and resistor. Like you have voltage, either voltage source in series or current source in parallel. Source transformation simply is changing the format of your source from voltage to current or current to voltage. However, your resistor is still this. I mean, you don't remove the resistor. Resistor is part of the circuit. If it's a voltage source, it remains in series. If it's a current source, goes in parallel. That's the only change.
And that's why 6 stayed right there, right?
Yes. So in this case, let me focus on this part. Since it's a very, very good technique, I want you to really learn this source transfer. It will really, really help you a lot in many circuit analysis problems. So for example, let's just focus on this small portion rather than complete circuit. Okay, originally we had a voltage source. Originally we had voltage source 6 volt and 3 ohm. Okay. And then from this side we had 12 volts. We had 12 volts and 6. I'll change this one to a current source in parallel. Extend the line, and I change this one to a current source in parallel. This series to this combination, this series to this combination. Now let's put the value. Voltage source becomes a current source minus 2 plus up. 6 divided by 3, 2 amp. 3 remains the same. And this one, move your hand. It's moving to your left, moving down, moving toward this terminal. Moving toward this terminal, so it's going down, moving toward the terminal current. So it's 12 divided by 6 equal to 2 amp, and 6 ohm remains the same. So what you have here is 3 ohm, 6 ohm, 2 amp down, 2 amp up. Then 2 amp up, 2 amp down, they cancel each other, so you eventually get only 3 ohm and 6 ohm, and 3 and 6 in parallel becomes one resistor, which is 2 ohm. So notice that by source transformation, I can go from 1, 2, 3, 4 to one element.
I find this more simple than nodal and mesh, in my
Yes,
opinion.
yes, yes,
Are you going to tell us in the test when we
Yes.
use superposition and when we use the other methods?
yes. You have to, because there are some techniques, like I don't know if you're in, but in electrical, in future, you have transformers, power circuits. In electronics, you have electronic circuit. You cannot use source transformation. If the format of a circuit is in such a way that you cannot use source transformation, it's not matchable with source transformation, especially with transformer. You have to use mesh. So that's why you have to know all the math. There are some circuits that you have like a node within a node within a node. It's crisscrossing line. You cannot use source transformation. Is when you have a voltage. Many circuits, especially at 2040 level, you can handle source transformation. As a matter of fact, next topic, which is Bevan and Norton, textbooks, they make it way too complicated. By source transformation, I'll show you. You can reach Bevan and Norton in 2 steps. However, if you follow textbooks procedure, it takes several steps to reach Bevan and Norton. So source transformation is a very, very handy method. I do advise that you keep it in mind, and in future, if you need any circuit, always check to see if you can apply source transformation, because you don't even write any equation. I'll show you here. You can compare it out, because I'm going to apply nodal mesh later. I'm not writing any equation here. I'm just making transformation, simplify to 2 ohm. The next step is that I can go now and erase this entire part. This entire part. The only thing about source transformation is, especially at the beginning, each time you should keep drawing circuits, so new circuits. So, oh my God. This entire part, I can substitute by 2. Okay, we're not done yet. You have to find IC. Now I go to this section and apply source transformation. Now I go to this section and apply source transformation. So it becomes the current source going up and 2 ohm. It's 12 divided by 2 equal to 6 amp and 2 ohm. 2 ohm, 2 ohm, 4 ohm, I0, and 2 amp. I still have this one. 6 amp up, 2 amp down. It's not all the way parallel. So what's the net? 6 minus 2 equal to 4 amp up. 4 amp up. So I have 4 amp up because 2 down, 6 up. Then I have 2 ohm. Then I have 2 and 4. And the question is I0, current division. That's the only formula you write at the end. I0 is the same current. What's the total resistance here? 6 ohm. What is I0? It's the other resistance. 2 ohm divided by 2 ohm plus 2 plus 4. Multiply by total current. Notice just by changing the format of the circuit, I could find I0. The original, if you remember, the original picture looked a bit messy. But by source transformation, and this problem was a perfect match for source transformation. Sometimes it's not, there is no match. There are some problems in the book I can show you. If there is no resistor in series with voltage source, or if there is no resistor in parallel with current source, you cannot apply source transformation. So that's why you need this. Any question about source transformation? In order to practice nodal mesh, or review actually, I'll do the same problem with nodal mesh.
Professor?
Yeah.
Should source transformation be like the first thing, the method we think of before we try anything else?
It depends on the person. I'm the one that I always think about source transformation immediately. Anytime they ask any circuit question before I jump to anything, I think, can I use source transformation to get my answer? And if it's just, I just do it by quick change. But of course, some people, they're more comfortable, let's say, with mesh. I know many people. First of all, you have to check to see if source transformation is doable. As I said, I can show you some problems that source transformation is not doable. And it doesn't do anything. One example is, let's say, I'll come back to this example. Let's say you have this problem. This is also from the book. This problem. Source transformation doesn't do any. First of all, you have to be careful. I mean, it's doable, but you have to be careful. Actually, you have to do the node, like this is node A, node B. For node A, you can go to source transformation, voltage source. Node B, you can go to source transformation, voltage B. Let's see. So this is node A, node B. And then you have a current source. And then you can go, depending on the question, you can also go to source transformation here. My point here is, if you can recognize how to do the source transformation, it's easy. However, there are many people that they get confused on how to apply source transformation correctly, which elements to combine. So if you know how to do it correctly and how to keep track with the question, yes, source transformation is a simple one. In exam, I'm not going to give you, I don't know, complicated situation. It's going to be very straightforward source transformation case, just to practice the method. But I'm talking in general, in circuit analysis, there are many people, especially when you have multiple loops and then branching off from here, going someplace, sometimes when you want to think about source transformation, you don't know how to start. Nodal, you know exactly how to start. The advantage of nodal mesh, they are systematic. You go to essential node, you assign nodal voltage, you write nodal equations. Source transformation is not systematic. Like it depends on your observation of the circuit and identifying proper elements to combine. So it's a little bit like a random situation than systematic situation. That's the only problem with source transformation. There are many student electrical engineering, good students, like senior students, in when you ask them to solve this problem with source transformation, they don't know how. I mean, they, as soon as you ask them to solve a problem, they immediately jump to nodal mesh, because it's like a cookbook procedure: step 1, step 2, step 3. Okay, let's go back to the problem and try nodal. See if you still remember nodal. Again, nothing else, just nodal. The good thing about nodal is you don't have to think about which branch should I combine, or just a straightforward. I'm drawing the same circuit, so you don't have to repeat. Somebody use nodal, this method. Practice nodal. 2 and 6 ohm.
Professor?
Yeah.
There's a drill going on here at school, but I don't want to miss the notes. Is there a way that I can get the notes through email or something?
If I use example, okay, let me write down. I'm making. Is it going on? Still going on?
Yeah, it says for 2 minutes. They send us a text message, but I'm not in campus.
Or 2 minutes?
Yeah.
Maybe I should wait. And if it goes away, I'll continue. If it goes away and finished, let me know. I'll wait about a few minutes.
Okay, thank you.
Professor, our exam is November 2nd. What chapters is going to cover?
Chapter 3, 4, 5, and maybe 6 or not. Nodal mesh, op-amp superposition, source transformation. For sure, 3, 4, 5. I mean, part 3, part 4, part 5. When it's done, please let me know.
Professor, I have a question.
Yes, go ahead.
Well, it's just a general question. What's the difference between your online lecture and your in-person lecture?
In person, I don't know. I see students if they're okay. Main one is the fact that at least I can control if the students are listening to my lectures. So even if they are not getting involved, I don't ask usually questions from the students in class, because if they are listening, I'm fine. I mean, they are not allowed to have any iPhone, any smartphone during lecture. They cannot use computer during lecture. They have to just listen. They cannot leave the room, come back. 75 minutes, they have to stay in class. And during exam, all my exams are closed with closed note, but you can bring cheat sheets, like 2 cheat sheets. No usage of any book or note or note, or for sure phone, smartphone. That's my main problem with online. So students, they don't get distracted, because online, how do I know? Students, they can even, when I take all, they say yes, but how do I know if they are busy doing other things? So I'm not sure if they are paying attention to the lecture, but at least for my in-class exam, I mean, in-class lecture, I pause a lot because students ask, and when the students ask question, I show it on the board, and then I look around, and other students, they also participate to answer the question. I think it's more effective learning. I mean, in engineering, and also I see the student, I get to know students, and it's much easier for me to write, for example, recommendation letter. And then the probability of cheating is very low. We have proctor, their in-class exam. We check to make sure that they don't have exam paper and they don't have any other extra help from outside. Cheating, not just for me, that's not my complaint. Many, pretty much 100% of faculty. When we have meeting, not just our school, in general, when I'm attending some Zoom meetings with other universities, that's two main concerns. Number one, cheating during exam, and that's unfair to those who study. And number two, because I can control check, because there is a center here during the exam to make sure that the students are not, my questions are not posted and checked during exam. That's one thing we can control. The other thing that we can control is, of course, we have proctor, we see the students, they cannot use their phone to contact people. And also we can control the learning process, because I can see the students are paying attention to the lecture and they are not thinking about other things or not doing other things. Those are main concerns. I do not personally see any advantage of online, except of course, not dealing with traffic. You don't have to dress up to come to school. You may save some time, but there are many disadvantages. So I don't know, this is just my personal thinking. My classes, my lecture, they don't change. I just lecture on the board, but I think I use more examples on the board. With online, I'm a little bit hesitant because, again, as I said, I don't record my lecture, and I do have my own reasons for not recording, and I don't want to bore you with that. But that's why I'm kind of hesitant. I think it's a bit unfair to students if I keep using examples from outside, and maybe it's more difficult for them to write down quickly. I slow down a little bit in in terms of writing. And then I can keep my work on board. Like, for example, right now I could keep, let's say, source transformation, not erase it, and go to the other side of the board and do nodal, and then go to the mid section and do mesh. I don't know, it's just for me. But the main difference is online, people are not allowed to use phone or computer. They should be in class. I do take attendance. And after a while, I do see people, I do know them by face. So even if they don't attend, even if I don't take attendance, I know that they were not attending. And exam, that's unanimous, all faculty. We are much better. We can control much better in-person exams than online. That's a known fact. Problem here is, since you mentioned that, and since I have a few minutes, when the students, they take upper division, it's not just electrical, pretty much all courses. We can tell if the core or background education was through online or through in-class. I'm not saying you guys, but in general, if the students, they have their background, like in math, physics, science, all classes, through online, that's not just my observation. They struggle a little bit more when they go back to in-class. Eventually, work doesn't stay this way. People have to go back to in-person. They struggle more. But the students that they have, even with low grade, they had been exposed to math, physics courses in person. They are a little bit more comfortable when they take upper division courses. But again, I don't know, some faculty, out of convenience, they still prefer to go online. Okay, the drill is gone, right?
No, they actually had us evacuate the building.
Oh. Okay,
No, the
maybe
drill is
okay.
ticking.
20 minutes probably, right? Okay, so what I'm gonna do, I'll probably, what time is it? It's 10:31, 10:40, we finish lecture at 10:40. I'm gonna send this example doing all four methods by mail, but for those of you who are listening online, I'll do it here, but I promise that I do it with nodal mesh superposition and source transformation as a wrap-up example. Okay, so
Thank you, Professor.
no problem. I'm not going to start Thevenin nodal. I'll just continue this with nodal. I have time to at least write nodal equation, and then I'll do nodal mesh superposition and source transformation, write it down or type it or something, and then send it to you. It's going to be this example. Okay, let's do with nodal. Okay, nodal, you have to identify the reference. Forget about the question. Remember, the question was I0. Question still I0. So forget about the question. Reference, essential nodes. We have essential node, the whole thing here. 1. We have essential node 2. We only have 2 essential nodes. Then you assign current to passive elements. Any passive element, you assign current, but you don't label. For essential node, label them. So this is V1, and this node is, we call it V2. We need 2 nodal equations to solve this problem. Okay, let's go to node 1. Current. No problem. We have 4 currents. All of them leaving. Notice that this current is the same. This is the current. 1, 2, 3, 4 branches connected to node 1, all of them leaving. Let's just start with easy one. 2 amp is leaving, plus, what is this current? The voltage at this end, which is V1, minus voltage at this end with respect to ground, which is 12 volts, divided by ohm here, 2 ohm. The current here, actually, I can switch for nodal. I can switch, these are in series, right? I can switch these 2. So I can redraw this one. I can redraw this one. It's the same. You don't have to, but it's easy to do. I can redraw this one by putting 3 and my voltage source here, plus or minus 6 volts. It doesn't matter. This is the current. Okay, what is this current? Voltage at this node, plus V1 minus. What is this voltage? This voltage connected at 0.5. It's 6 volts higher than V2. So it's minus 6 volts higher than V2 divided by the resistance 3. So the voltage at this node minus the voltage at this node, you have to use the immediate nodes. This node is 6 volts higher than V2. 6 volts higher than V2. So it's V1. This voltage is V2 plus 6 volts. V1 minus V2 plus 6 volts divided by 3 ohm. This is also V. What about this current leaving? This voltage, because it's connected to minus, it's 12 volts lower than V2. So this voltage is 12 volts lower than V2 because it's connected to minus, V2 is connected to plus. So it's equal to V1 minus V2 minus 12. This point is 12 volts because it's connected to minus 12 volts divided by 6 equal to 0. Okay, so this is equation 1, nodal equation 1. Nodal equation 2, again, we go to node 2, 2 currents. Entering 1 current is leaving. We have already discussed this current. It's V1 minus 6 plus V2 divided by 3. The other entering current we have already discussed, V1 minus V2 minus 12 divided by 6. equal to the current leaving from where? V2 to ground divided by 4. This is equation 2. So you simplify these two equations, multiply the left side, multiply the left-hand side and the right-hand side by common denominator 6. So I have 2, equation 1 becomes 2 plus 3 times V1 minus 12 plus 2 times V1 minus V2 minus 6 plus V1 minus V2 plus 12 equal to 0. And then you group V1 together, V2 together, you get V1 plus V2 equal to something. Equation number 2 multiplied by 12, you get 4 times V1 minus 6 minus V2 plus 12, it's 2 times V1 minus V2 plus 12 equal to 3V2. Again, you write it as V1 plus V2 equal to something. Kramer's method or substitution. So from nodal, you find V1 and V2. Now, how do you answer the question? Now you go back. After you find V1 and V2, you go back to the question. You go back to the question. The question is I0. This is I0 question. I0 is the current passing through 4 ohm. I0 is equal to V2 minus 0 divided by 4 ohm. By the way, when you're solving two equations to a node, go back to the question. For question, you don't need V1. So actually, you don't have to find V1 here if they ask you to find. And then from here, you find the current. This is no. Any question?
So to find V2, we need to use equation 1 and 2, right?
Yes. You can either use Kramer's method or you can use substitution. Like, for example, find V1 from equation 1, put in equation 2, and then find V2.
Thank
And
you.
even if you're using Kramer's method, remember we are forming 3 deltas. One overall delta, delta 1, delta 2. You don't need to form delta 1 because you don't want to find V1. You just want to find V2. So you only form delta 2 and delta 2 divided by delta equal to V2.
Yeah, just 3 deltas.
Yes, yes. Okay, I can also do it with mesh and superposition, but because of timing, I'll show it. I'll do it in, write it down. And because of people who didn't attend, I'll send it to all. I finished methods. Now we continue with you can see the application of source transformation. Like good, you appreciate source transformation when we cover the next part. If you read the book, they make it way too complicated. It's very simple. I give you many good shortcuts. It's very important, essential. Let me give you background about what we cover next time. Anytime you go and buy electric devices, electric equipment or something. Okay, they give you a brochure or catalog. Nobody gives you the circuit. Like, let's say you're buying anything. Nobody shows the circuit, analog, digital. They just give you some data. Data means the key information. For example, what is the power consumption? What's the total power produced? Okay, the concept that we cover next time is based on the following. Suppose you have a black box. Inside black box, you have many elements. But the output of the black box is something that you're using. And you need to give some information about the inside. First of all, many people, they are not like circuit expert. And nobody shows that. Many people, they don't even know the exact. And many circuits are digital anyway. Integrated circuit anyway. So you just give the key information. The next chapter concept is based on, is it possible? That happens in power. You have several transformers, you have like a power generator, you have everything, and you want to test a load. They call it in power system, you want to test a load. But in order to do testing, you're using computer simulation. For computer simulation, you need to connect the load to the circuit and measure the current voltage energy. However, this original circuit is way too complicated. You don't need all the information. You don't need detail. I don't need to know this voltage to know this current. I just need to exiting current or voltage. I don't need the detail inside. So why not substituting this entire network by two simple elements, either voltage source in series or current source in parallel? Is it possible that you take the entire complicated circuit and substitute only by two elements? And anytime you want to test this box by simulation or by hand, rather than drawing the entire circuit, you just put the voltage source, resistor, current source, resistor. This voltage source in series or current source in series, they fully represent the main circuit. However, remember, when you do that, you lose track with detailed information. You just have overall information. This is called Thevenin Norton model. And it's pretty much anything you do in electrical engineering when you're dealing with black boxes, when you go to the lab and you're dealing with some equipment and you just connect to the output terminal. The inside, information inside about the inside is given only by two key numbers. And those two key numbers come from the fact that you can substitute the entire box by two elements. This is something that I'm going to continue and cover next time. It's called Thevenin Norton equivalent model. If you have any question, please ask. Otherwise, have a good day. I couldn't take all because of the
My question was on the last equation. When you were finding your essential nodes, I was kind of confused on why you chose those two essential nodes.
Essential nodes, because essential node, remember chapter 1, we define essential nodes. Essential node is a node that, when you look at this circuit, when we define essential node is a node that you have two or more elements connected. This is your reference. Okay, look at this circuit. Find the nodes that you have more than two elements connected. One of them is this one, and one of them is this one. Maybe we have 1, 2, 3, and for this one we have 1, 2, 3, 4. Essential node is a node that you have three or more connected. Three or more elements connected. So we have node 1 and we have node 2. For nodal analysis, you have to find two essential. And then we assign current any direction to any resistor in the circuit. So this was the preparation process for node 1. Essential node, you have to check your circuit to see which nodes, other than reference, which node has three or more lines connected. If that is a node with three or more elements, then it's essential node. And then it's the node that you're using for your node.
Okay. And you uploaded the homework answers, right?
Yeah, yes, for number 5. And I'm going to send maybe tomorrow solution of this problem for this problem using all 4 methods.
Okay. Thank you.
Okay, any other question?
Yes, Professor, just real quick. It's based on the op amp and the essential node is kind of similar. The line that comes out as the output, that doesn't count as a line towards the essential node, am I correct?
Yeah, for output, you don't assign. Okay, if you have the op amp, let's say here, let's say this is a line, and then it goes to another op amp. Any output that directly is connected to any output, that it's directly connected to the op amp, you just assign the out, but you don't use it as essential node for node. No.
Okay, perfect.
Okay.
All right, thank you.
Okay, sure. Okay, have a good day.
Thank you, Professor. Have a good day.
Thank you.